Section 215.2a of the NEC tells us that feeder conductors shall have an ampacity not less than the larger of 215.2a1, continuous and non-continuous loads, or 215.2a2, ampacity adjustment or correction factors. The size of the primary feeder conductors of our transformer is based on non-continuous loads. To determine the primary feeder conductor size, we'll use Watt's law to calculate the ampacity of the transformer's primary side feeder. To do this, we'll need the transformer's kilovolt amp rating and primary voltage, which are found on its nameplate. We see that the rating is 50 kilovolt amps and that the primary three-phase voltage, phase-to-phase, is 480 volts. These are the values we'll be using in our calculation. Watt's law is expressed as P equals I times E. The power, or P, in watts is equal to the current, or I, in amps, multiplied by the voltage, or E, represented in volts. To solve for the ampacity, we express the equation as current, I, equals power P, divided by voltage, E. Now let's plug in the values from our nameplate. For power, we use 50 kilovolt amps. Knowing that 1 kilovolt amp equals 1,000 volt amps, we express 50 kilovolt amps as 50,000 volt amps, or watts. For voltage, we use the primary phase-to-phase voltage, which is 480 volts. And because it is three-phase, we multiply by the square root of 3, which is 1.73. This gives us 830.4 volts. Then we divide 50,000 volt amps by 830.4 volts, which results in 60.21 amps. This is our ampacity. Now we go to table 310.16 to determine the conductor size. We'll be using type THWN copper wire for this installation, which brings us into the 75 degrees Celsius column. Note that our calculated ampacity, 60.21 amps, is not shown here as a standard size. So we round up to the next standard size, which is 65 amps. We follow this row across to arrive at 6 AWG. This is the size of the primary feeder conductors for our transformer.